Welcome everyone to day 2 of this series. I'm not sure if you attended yesterday. So while people are filing in, I'll just spend a few minutes and um, just very briefly tell you what we covered yesterday. And I'll also tell you what we can expect to cover today. All right. And I'll also introduce myself just in case there are any newcomers here. So as you know, this is a 2-day series. We covered machine learning yesterday. Okay. So what did we do yesterday? Well, we really did a whole lot. But really my goal for yesterday was to help you understand that machine learning is something which it's not rocket science. Yes, you have to do a little bit of hard work to get on, but if you have anyway decided to be in the um, tech domain, then it's not a big deal at all to absorb the basic elements of machine learning and start contributing. Okay, that was my message for yesterday. And towards that end, I helped you understand, I sincerely hope I helped you understand how simple situations can be formulated as machine learning problems and how you can compute the solution to that machine learning problem. Okay, we talked about classification. We also talked about clustering. Okay, so and I helped you understand how some of those algorithms work. Okay, so that's what we did yesterday. And just a brief couple of words about me in case you did not attend yesterday. My last name is Sathyanarayana. See how it rolls off my tongue, but you can call me Shashi. Okay, so what do I do? Well, I've been very fortunate in being able to participate in very, very interesting projects on machine learning and related topics. Sometimes not machine learning, but equally interesting topics on in signal processing and image processing. Okay, so as numeric insight, I've been picking up projects and really learning a lot. Okay, so that's one thing that I do. Another thing that I do is I teach, and my students are my inspiration actually, because they help me to understand how important it is to communicate clearly. I know I have an accent, but I hope that I compensate for that accent by speaking very clearly. Yes, my students have taught me how important it is to communicate clearly, and that is important even if you're not a teacher. I'm sure we all recognize that. And I think teaching really keeps me always constantly reminded of the need to communicate clearly. Okay. So as part of teaching, I teach for companies and I also teach at UC, University of California. And talking about teaching for companies, I'm about to complete a series that I have been doing for Visa Research. You know, Visa is the credit card company. So they are interested in text processing and natural language processing, which in fact is the topic for today. So I've had a really interesting couple of months interacting with the good folk at Visa Research and trying to create examples and solutions which they might find useful. It's a customized course. It was meant to be such. Okay. And before this, I did a series for Walmart Labs that was more of a basic foundational course. And as you know, Walmart Labs is, I hope they won't mind if I say that they are competitors of Amazon. They are an e-commerce site as well. So lots of machine learning there. Okay. I'm also going to do a series for another company which unfortunately I cannot disclose right away. And they are in communications, and they are interested in machine learning for signal processing. I do have a signal processing background as well. So that's what I do. And I'm going to finish up this slide right away just by telling you that I do teach at UCSC, that is University of California at Santa Cruz. And the next session starts just in a few days. Okay. And if you're interested, you can take a look at the website. Um, if you were to go to the UCSC extension website, you can see um, all the offerings, not only offered by me, but also my colleagues who are also very talented. And you can get to know about those courses. And I hear that there is a discount being offered on every course now in view of the current situation. Okay, so it says 25% off. All right, so you might want to take advantage of that. Sorry for this shameless plug here, but it's also a plug for UCSC in general. Okay, so let us keep going. We are done with this. Now today is going to be quite different from yesterday. Okay, yesterday we had PowerPoint. Today we are not going to do PowerPoint. We are in fact going to dive into code. And I hope to convince you that natural language processing is something that you can actually get into. You can get your hands wet, and it is not overly complex at all. Okay, so that's my goal. And you can do a lot of useful stuff if you just invest a little bit of time and effort in absorbing the basics. You can really do exciting things. Okay, that's my goal. Now I'll just take a look at this chat panel. um, okay, all right, there is a Q&A here. So I hope this question has been answered. There is a question: what is the prerequisite of the machine learning for professionals class? And I'm sure that Monica or Ilse will provide a correct answer to that question. Okay. Off the top of my head, I do not know. Right. So let's get started, really. I want to assure you that this material is going to be available to you. Okay, I do not know if it's going to be available today. I'm going to send it across. In fact, I've already sent it across to UCSC. So based on their protocol, they're going to package it somehow and send it across to you. Okay. Do not worry at all if all this code goes over your head. It doesn't matter. Okay. But I want you to just appreciate that even though it is not exactly written in speaking language, it is still quite comprehensible. And if you know any programming at all, not necessarily in Python, but any other language as well, you're still going to follow this. And if you already know Python, well, yay, good for you, because you can take this code which I'm making available to you, and you can play with it and extend it, make it do more spectacular things. All those things are very much possible. Okay. And let us do one thing now. I'm going to go just very quickly go over the table of contents here. Okay. So that you get an idea of the overall organization of what we are trying to show here. Okay. I'll go over the table of contents, and then I'll go over each section in detail. Okay. So I hope that sounds good. Let me just steal a look at the question board here. We are good. All right. Although this says question. Okay, thanks. I'm software engineering. Good to know. Okay. Excuse me for a second because something I had kept here suddenly disappeared. Okay, I got it back. All right. So a quick run through of the table of contents. What is our goal here? I'm going to demonstrate two very commonly encountered um, tools. Let me just call them tools, which you would use to do natural language processing. Okay. One is text classification, and the other is information retrieval. Okay. There are a whole lot of applications. Okay. I've just um, given you a list here. It's incomplete, of course. It's an incomplete list. But just to give you an idea, yes, you know, document proofreading, that is checking for spelling and grammar. Your Microsoft Word does that, of course. Word prediction, of course, Microsoft Word does that. Your cell phone does that as well when you're typing, even trying to type in a simple text. It suggests words. That's word prediction. Information retrieval. Actually, we're going to talk about information retrieval. You can imagine, let's say you have a library. When I say library, I mean a physical library. Okay. And you're the librarian. And let's say all of a sudden you receive a new book. You have to make sure that that new book goes to the correct shelf. It goes to the correct position on the shelf. It goes to the correct place. That is, there is a specific place next to some other books that it should sit. Okay. So all of that is text classification, right? So text classification is essential in many situations such as this. Okay. So information retrieval, um, I'm sorry, this is code, so I should not double click there. So we have information retrieval, text classification, text summarization. Okay. That's very interesting that you can do text summarization. How does a machine really understand an entire chapter or even an entire book? How does a machine understand the entire book and effectively summarize that book using a few sentences? It seems very mysterious, right? Actually, it's not all that mysterious. If you remember a key point from yesterday's talk, okay? What was that key point? I'll just show you that key point. Uh, let's see. Let's look at this, okay? If you did not attend yesterday, don't worry about this. All that you need to appreciate is that data, every piece of data, also known as a sample or a feature vector, every small piece of data is really a point in multidimensional space. Okay, point like what I'm showing you here. Okay, so if you have an entire book, say today's bestseller, if you have that entire book, you can think of every sentence as a vector. Okay, so every sentence is really a dot, such as this. Okay, and if you have a large collection of dots, I'm sure you can visualize in your mind that large collection of dots. It looks like a cloud. That cloud is going to have a centroid. Okay, so that's very interesting. That centroid is also a vector, right? Now, if you think about, let us say, 25 dots, which are the closest to that centroid. Okay, 25 dots, which are closest to that centroid. If you consider that small set of 25 dots, and if you consider the sentences corresponding to those 25 dots, which are closest to the centroid, then those 25 sentences might very well be a summary of that entire book, because that's closest to the center, right? Closest to the center, or closest to the central concept of that entire book, right? So there's a little digression. I hope I helped you understand um, how is text summarization possible, okay? So once again, once you know machine learning, and I should point out that in order to be able to effectively do natural language processing, you can do it effectively if you know machine learning, if you are familiar with all the concepts, the tools, and shortcuts and packages, workflows, and so on. Okay, so that's another reason to attend a class in machine learning first, or you're most welcome to read on your own if you have the motivation and the time. Okay, so once you know machine learning, then all these concepts, such as every sample is a vector, and if you have a bunch of vectors, you can find the centroid. All these concepts seem so natural, and you can do all of this wonderful stuff. Okay, you can do question answering. Question answering is in a way the same as information retrieval. Okay, if you have a bunch of pre-composed answers, then all you need to do is match a question with a pre-composed answer. Okay, this is what happens in so many bots that you might have encountered. Okay, so these are all various types of applications, right? We are going to explore text classification and information retrieval. And when we say when we say text classification, once again to reiterate, we are talking about having a lot of text, and associated with each unit of text is a category. Okay, so you should imagine that you have a data set, a training set containing pieces of text and their associated categories. Now, if you're given a new piece of text, you should be able to place it into one of these categories. That is text categorization. As I said, library, yes, I think you understand. Information retrieval um, refers to, for example, a search engine. Okay, you type in some keywords, and the system should pull up a ranked list of relevant documents. We say documents, they could be websites. Okay, they could be some entities, right, which are pulled up. So that is information retrieval. So we are going to briefly touch upon these two here today: text classification and information retrieval. Okay, so let me just take a quick look at QA. When would you use RNNs for NLP versus machine learning techniques for NLP? Um, Let me just answer this question right away and tell you, yes, recursive neural networks, I'm sorry, recurrent neural networks are a type of machine learning algorithm. Okay, so it's not NLP, it's not RNN versus machine learning. RNN is machine learning after all, and it is very likely that you would use a specialized version of RNN called LSTM. Okay, you must have heard of these terms, but let's not get too worried about all of those. Let me generalize this question that um, this person is asking me. The question is, when would you use neural networks for natural language processing versus traditional techniques? Okay, I have just slightly expanded that question. And my answer, all, all these types of questions have only one answer from me, at least. Okay, If you can get away without using neural networks, please try your best to do so. Okay. Use neural networks if their use is truly justified. Okay. Because very often, if you need a solution which is explainable, which is very robust, and which offers some performance guarantees, then neural networks are not your solution. Okay. You can really do wonderful things with neural networks, but we have to be aware of the limitations and the warning labels that come with the use of neural networks. Okay. So that's what I can say about this question. And there's a question being asked to student services. So I'll leave that to Ilsa and Monica to answer. Okay. So there is another question about, let me just take a close look at this. So when we say information retrieval, the question is, what is the difference between information retrieval and information extraction? Okay. So when we say information retrieval, that refers to finding the relevant information to a user's query, like Google search, for example. Okay. When you say information extraction, I think that is best illustrated by giving you an example. Okay. Let's say you write an article on Wikipedia. Let's say you write an article about somebody that you know, okay, who doesn't have a page on Wikipedia, but you believe that person is really important and deserves a page on Wikipedia. Okay. So all you have to do is just write that page, and Wikipedia is going to extract some information. Okay. Wikipedia is going to say date of birth and age, and it's even going to say spouses and so on, right? It's going to automatically fill in all of that stuff. So that is information extraction. That is, this natural processing algorithm is able to scan that piece of text that you have entered, and it's able to automatically extract key elements and populate a summary. Okay. You can try typing in the name of any famous person on Wikipedia, and you will note that it'll show you a quick summary of all those extracted entities. I hope I have answered your question. All right. So let's keep going now. There's another question. For the introduction to machine learning course, what is the ratio between mathematics, programming, and practical application of ML? It's quite difficult for me to answer this question because let us just say that it is 30, 30, 30, equal measures of everything, really. Because in order to be able to do effective applications, build effective applications, of course, you should be able to program. Of course, you should be able to understand the algorithms so that you can use them effectively. So I do not really, as far as my class is concerned, I pay sufficient importance to the mathematical component. I personally believe that that is what will help you differentiate yourself from other people. In fact, the vast population who don't care too much about the mathematical content of the algorithms. Okay. So in my classes, I do make a point of demonstrating how if you are unaware of some mathematical detail, you would not be able to use some algorithm as effectively. Okay. And the difference sometimes can be very huge, really. Okay. So that's my answer to that question. Let's keep moving along. I said I'm going to take you through this table of contents. Okay. So what we're going to do is talk about text classification first, and then talk about information retrieval. So talking about text classification, I'll just pull up my, there are, see, as I told you today, we don't have PowerPoint today. It would be a huge waste of time. But on the other hand, I'm going to scribble some stuff here. Um, excuse me for a minute. Okay, I'll just use this as a whiteboard just to make some points here. Okay, and I believe all of this stuff is also going to come through in the recording. Okay, so when we say text classification overall, this is what we mean. Okay, so we have the classifier and we are going to feed in text. Okay, a block of text, for example. Okay, so before we can actually feed it into the classifier, there is some pre-processing. Okay, there is some pre-processing required, and then it is fed to the classifier, and the classifier is going to give you the result, which is called a class label, right? So we saw this from yesterday. Okay, in order to make this possible, this classifier has to be trained with a training set. And in natural language processing, a training set is called a corpus. Okay, so you have a corpus, and in our case, a corpus is going to consist of a long list of documents. Okay, and each document has a category associated with it. It's a class label. Okay, I'll show you what the class labels are, and I'll show you what a few of those documents are, just to give you some flavor. Okay, I'll show you those. And as I said, we need to do some pre-processing. Okay, so all of these steps here talk about pre-processing. Okay, and something else that I already told you about is that if you're going to feed some things to a classifier, you need to make sure that ultimately the classifier is only going to see vectors, right? So there is something called vectorization that comes over there. Okay, so we're going to talk about vectorization. Okay, and finally we talk about the classifier itself. Okay, so there's some little bit of detail here which I'll come to when we get there. Okay, so I hope the overall flow is clear as far as text classification is concerned. We'll talk about pre-processing, we'll talk about vectorization, then the classifier, and finally we will take a look at a few examples and convince ourselves that it is working. Okay, we can either take a few examples or we can compute the accuracy of the classifier and get a sense of where are we? Is it good enough or not? We can check that, right? So that's what we're going to do. As far as information retrieval is concerned, this is going to be a relatively smaller topic. Okay, it actually in principle is a much bigger topic, but I have really reduced it to the barest minimum. Okay, just to fit it in within this next I think we can keep going for approximately 45 minutes. Okay, and to allow some time for discussion and questions. Okay, so let's keep going now and talk about pre-processing. So before that, I want to tell you something about this uh, environment that you're seeing here. I'm quite sure that at least some of you know that what you're seeing in front of you is called a Jupyter notebook. This is Jupyter. Okay, So this word Jupiter stands for Julia, Python, and R. Okay. Um, in fact, this logo is supposed to represent Jupiter with some moons circling around it. Okay. So this is a Jupyter notebook. In my opinion, this is a wonderful, wonderful environment to not only write programs, but also document your work. Okay. So this is what you're going to get. So it's going to have all these comments and explanations. I tried my best to make it as um, rich with comments as possible. Okay. So you can do a whole lot of stuff. And to get started, we need to import some basic packages. Before I forget, I should also tell you one thing. Um, it is possible, of course, what most of us would do is we would install Python and Jupyter, etc., on our own computing platforms, on our own desktops or laptops, okay, so that we have total control. But if you do not want to, because it may be a little difficult to do so, it may be difficult for you to um, install those pieces of software. There is another method, okay? What you can do is you just do a search for Google Colab, C-O-L-A-B, Colab, okay? So Google Colab gives you a Jupyter network in the cloud. So you don't have to install anything. You not only get all of this stuff for free, all you need to do is have a Google account. You not only get all of this stuff for free, but you also get very powerful computers, okay? So those computers not only have GPUs, but they even have TPUs, which are tensor processing units. So you can run some uh, very extensive computations, which would be very time consuming to run on your laptop or desktop. So there is that possibility. So please keep that in mind. And you can just Google Colab, Google Colab, and you will immediately know what I'm talking about. Okay. So let me just take a quick look at a question. So Jupyter Notebook can easily translate Python to R and vice versa? No, no, no. Uh, to the best of my knowledge, I don't believe any tool exists that can cross convert between uh, languages like Python and R. All it means is you can use Jupyter Notebook to do Python programming, or you can use it to do R programming or Julia programming. And I think there are also a few others which are not part of the name Jupyter. Okay, so that's all it means. Okay, so I hope I answered that question. You need to import some basic packages. Okay, so I have listed all the packages that you need to import. Okay, so this is part of the programming philosophy with Python. Okay, which is that you get a basic environment which has some minimum functionality, and depending on what you want to do, you have to make sure to install those packages and import them. Okay, so how do you know what to import? Well, that's a great question, really, but I can tell you that if this question stumps you, it's only going to stump you for a maximum of 1 day or 2 days, no more than that. Okay, so it is such common knowledge that um, if you just take a look at some few examples easily available on the internet, GitHub or something, you will easily understand what packages that you what packages are available to you. Okay, Python has a very rich ecosystem, so plenty of packages, and that saves you a lot of work, really. So code reusability is very, very big in Python practice. Okay, so we must embrace the dry principle. Dry refers to don't repeat yourself. Okay, when we say don't repeat yourself, what that means is don't try to write code for something that has already been done and packaged. Okay, so if you do that, you are guilty of offering wet solutions. Wet refers to write every time, write everything twice, and so on. Okay, so we need to be dry and not wet. That's why you need to import all these packages. And I've just added some small notes here to just tell you what those packages do. Okay. Um, so here's a question. Is there a dependency graph that shows the prerequisites for the machine learning related classes that you offer? Um, I'm not sure if there is a very formal dependency graph, but if you were to click on the links for each course that you might want to take, that's going to tell you what the prerequisites are. Okay, so I hope I answered that question, but student services may have more to add to that. Okay, so we are done with imports. Okay, if you want to import data, well, I'm giving you some data. Okay, I'm going to make this available to you along with this code. So you get this code and also the data file itself. You will notice that the data file has this extension PKL. Okay, that stands for pickle. Okay, the data is pickled in that file. Okay, you have to make sure that that file is also placed in the same directory as this notebook. Once you import that file, once you read that file, then all of that data is available in this environment, in this notebook. Okay, we can take a quick look at what that data looks like. As I already told you here, that data, that is that corpus, has class labels and text. Okay, so you can think of this entire thing as a matrix. The data matrix, you can see, has some 5,000 or 4,991 entries, and every entry has two elements. Okay, the first element is the category label, and the second entry is that actual text, that block of text. Okay, so you can see that there are these there's a lot. I cannot show you all the thousands of rows, so I'm randomly showing you some 10 rows. Okay, you can play with this just to get an understanding of the types of documents there are. Okay, you have biology, philosophy, evolution, commerce, and so on. All right, so here we are examining the unique categories. Okay, there are documents and each document is associated with its own category, but the categories are limited in number. Okay, there are 10 categories and I have listed them here. Okay, and I got this list of 10 unique categories from the data itself. I just looked at the data and using these simple Python codes, okay, I am able to get the unique categories. I'm also able to get the counts. Okay, this means there are 500 articles on art, 498 on astronomy, and so on. Okay, so again, let's not lose track of where we are going with this. It's our goal really to somehow take each document here and convert the document to a vector. Okay, once we do that, we can apply machine learning, right? That's our goal. And we can generalize this as much as we like. Sometimes you might want to think of every word as a vector. Sometimes you might want to think of an entire category as a vector. All of those are possible. Okay. It depends on your application. In fact, it would be quite easy for you to do this experiment where you somehow create 10 vectors, one vector for each category. And if you do that, and if you look at these vectors, if you can somehow visualize these vectors, it is so amazing, I tell you. It will turn out that um, the vector for evolution, you will find, is very close to the vector for biology. And the vector for commerce and economics are close to each other. And the vector for art and literature are close to each other. And you also find I think this is very mysterious and also satisfying. You can also see that although astronomy and cosmology are very close to each other in this vector space, which you can actually visualize, although astronomy and cosmology are very close to each other, you find that philosophy is also somewhat close. Okay. It looks like philosophy has something to do with cosmology, all right, or astronomy, and that may be true, right? You can see all these interesting things once you master the art of converting either words or sentences or paragraphs or blocks of text to vectors. Once you can do that, really the sky is the limit. Okay. So yes, the session will be available as a recording. Um, so we just took a look at the data. It has been imported now. Okay. Now we want to do a whole bunch of pre-processing, right? Remember I told you that you need to do a whole lot of pre-processing and vectorizing. So when we say pre-processing in natural language processing, we typically mean that given a piece of text which looks like this, okay, I've shown it to you here highlighted. Ultimately, we want to simplify it and make it look like this, okay, like this, okay. I'll show you the original version, okay. This is the original version. It is very human readable. It has all these words which actually are not very informative, but without these words, we would find it quite difficult to read, okay. Words like a, is, as, and so on, okay. So this is the original, and after doing a whole bunch of pre-processing, we get this, okay. It's a much smaller set, and it doesn't have all these words like is and a and so on, okay. So that's the overall summary of pre-processing. Just to quickly take you through the individual steps, okay. First, you do something called tokenization, okay. Tokenization simply means you take this, okay, which is document number 15, and break it up into individual words. And when we say words, we mean words separated by any non-word, okay, like a space or punctuation or so on, okay. So if you convert this block of text to this list of tokens, then you have done tokenization, okay. And doing tokenization is very, very easy. All you need to do is take every document for document in all documents. You just keep on doing something called word tokenize, okay. So word tokenize is available to us. We don't have to worry about how do we do word tokenization. You don't have to worry about it because that is taken care of you you have, with a great deal of forethought, imported the natural language toolkit. Okay. Word tokenize is part of NLTK. If you imported NLTK, then you have word tokenize and a whole lot of other things as well. Okay. So that tells you how word tokenization is accomplished. Okay. After you do this word tokenization, if you're interested, you can find out how many unique tokens there are. Okay. Because there might be so many words that are common between documents, right? So how many unique tokens are there? You can find that out quite easily with just 2 lines of code. Okay. So if you do this, you see that there are some approximately 55,000 unique tokens. Okay. Um, there are a few questions. So I will deal with them later because, okay, I'll deal with them. I promise that I'll deal with them by and by. Okay. Because I'm becoming increasingly aware of the time and we do need to cover this material. Okay. And leave time for questions. So other important pre-processing step is to remove all extraneous words. You might have punctuation, you might have numbers, etc., etc. We want to remove them. Okay. How do we do that? Easy, because you can always do this loop. Okay. You take all your tokenized documents and you go over each document. And within each document, you only keep the words which are alphabetical. Okay. And then we are also converting every word to its lowercase counterpart, just to simplify the data. Okay. So ultimately you have got documents alpha lower. Okay. The difference between documents tokenized and documents alpha lower is an extra step of pre-processing. You have thrown away everything that is not an alphabet and you have reduced everything to lowercase. Okay, that's what we have done. And okay, I can answer this very quick question. If I use Collab, do I still need to download Jupyter? No. In fact, Collab is Jupyter. Okay, I hope it answers your question. But however, once you're within Collab, um, you cannot assume that all the packages that you might want to import are already available to you. Okay, you might need to install those packages. And how do you install those packages? Very easy, believe me. And I think you'll figure it out by yourself. There are enough resources on using Google Colab that you can easily get by. Okay. So that is about removing alpha. And there's another step here, which is you need to remove stop words. Stop words are non-informative words like a, an, of, etc. And we can use again NLTK, Natural Language Toolkits, stop words to take care of that task. Okay, so you can go over your list of, you can start from where you left off. Where we left off is documents alpha lower. Start from where you left off. And again, for each document in that set, you can make sure that you examine all the words and keep those words only if they are not stop words. Okay. I'm also doing one more thing here, which is I'm throwing away very short words, even if they are not stop words. If there are any words with just 2 characters, I'm just throwing them away. Okay. I might be risking something here. I might be risking throwing away some information, but that's very, very rarely the case. Okay. So ultimately, after you do that, you, for example, document number 15 now starts looking like this. You can see there are no stop words here, no punctuation, no numerals, right? So how many unique tokens remain after doing this? Some approximately 38,000, okay? That is much less than 55,000. So we are reducing the amount of data that we are going to work with, okay? We are throwing away data which we feel safe in declaring as non-informative, okay? So you have got about 38,000. You can still do something more here, which is you should realize that words like um, classify, classification, classified, or astronomy, astronomical, and so on are practically duplicates of each other. So why bother keeping all of them? We can just keep one of them, one of those variants, and throw away the rest. There is a risk, of course, that something bad will happen. But believe me, the risk is very small, and we can just cheerfully go ahead and pretend that it will never happen. You'll be quite good, at least for the purposes that we want to use um, this text classifier for. Okay, so that is called stemming. Okay, throwing away astronomical if you already have astronomy. Okay, that's called stemming. And even for doing stemming, we are using NLTK, Natural Language Toolkit. You can use something called a snowball stemmer. Okay, and there's a little bit of detail here which I'm skipping, because if you just use the snowball stemmer, then of course stemming takes place, but the resulting words are kind of very rudely chopped off. They're very rudely truncated. I do not like it. Okay, so I am doing something here. Don't worry too much about this, but all I'm doing is I'm making sure that after doing the stemming, we end up with some readable words. Okay, it bothers me if those words are not readable. I want to do stemming, yet make sure that the words are readable. So it's my little gift to you if you want to use this little uh, piece of code that I have here. Okay, so this is modified stemming. Hmm? After you do this stemming, we can take a look at the unique tokens now. Now it's come down to 27,000. Okay, and the total number of words that we have um, in the STEM documents, the total number of words is some 43,000, okay, of which you have 27,000 unique words, right? And you might think of this as very strange that we started with tokenization. Tokenization simply refers to you take a sentence and show it as a list of words. That is tokenization. But now we need to do detokenization. That's actually not a very deep detail. It's not very deep at all, but all it means is, you need to join them together and make it into one block of text. Okay. So here is document number 15, which has been detokenized. Okay. When we say detokenized, it only means, you see all of these, which were individual list elements, have all been joined together and made into one block of text. We need to do this because whatever comes next requires that the input be one block of text. That's why we need to do that. Okay. So we have done a whole bunch of pre-processing. Okay. So remember that once we build the classifier, we ultimately, if we are going to build a complete application, we want to have the ability to feed in a block of natural language text. Okay, here we want to feed in natural language text, and we want the class label coming out here. So if we want to do this, we better have a tidy block of code to do all the pre-processing, right? We want to have that tidy block of code, which is why I have this function here, which takes a block of code, which I'm just calling as query, okay? And it is doing all of this stuff, okay, in sequence. It is doing tokenizing, remove non-alphabets, remove stop words, stem, detokenize. It's doing everything, okay? And just to make sure it is working, I can take document number 15, okay? And if I pre-process, I'm getting this block of text, which you can see is exactly the same as this block of text. So it's working okay, right? So we are done with pre-processing. Next, we need to do the other thing that I told you about, which is vectorizing, okay? So I'm calling this section mathifying text with word vectors, okay? You know, my usage of the term word vectors here is correct, but it may be slightly misleading because when people say word vectors, they mean something quite specialized, but it's okay. I don't mind saying word vectors here, okay? Let me just take a quick look here. Um, so are there really 15,000 stop words in English, let alone in such a small corpus? Um, I'm not sure where we got that 15,000. Um, I never said that there are 15,000 stop words, but um, it's okay. It's much less really. Okay. Let me see if I can just quickly show you the stop words. So the stop words are here. Okay. It's going to be a long list. These are all the stop words. And if you want to know how big that set is, we can do this. 179 stop words. Okay. So definitely not 15,000. Okay. Whatever I did just now is a little risky because I find that in real time, especially when talking and trying to explain stuff, if I try to even do some small piece of code, very simple piece of code, I make a mistake and I look very foolish. So I'll try not to do that, but this worked. This time it did work. Okay. So I'm glad we got that sorted out. Let's move on to mathifying text with word vectors. Okay. We need to convert passages of text to vectors because machine learning algorithms expect numbers as input. Okay. So how do we do that? Again, we are going to use some packages. The packages are count vectorizer and TF-IDF vectorizer. This seems really terrible. You know, sometimes if you're new to a field of study or whatever, uh, you can be really bothered with the jargon, okay? And very, very opaque and arcane abbreviations. TF-IDF is one of them, okay? But I hope that once we finish, TF-IDF seems somewhat familiar to you, okay? TF stands for term frequency. IDF stands for inverse document frequency, okay? So these are concepts that you need to use if you want to convert um, text to vectors, okay? So without going too much into the details of this piece of code here, this block of code, I want to tell you that our goal is to take each document and convert it into a vector, okay? For example, here, this is document number 0, the very first document, and that is the vector representation of that document, okay? That first row is the vector representation of the document. So what does that mean really? It's very easy to understand. All it means is that that first document does not contain the word also. It does not contain the word art. It contains the word biology 6 times. It contains the word century 0 times. It contains the word economically 0 times. It contains the word evolution 2 times, and so on. Okay? It is just a count of the number of times each of these listed words occurs. Okay? But why am I only considering 15 words here? On the top here, you see, 15 words have been listed. Okay? I'm only considering 15 words just to show you this example. Okay, what I have done is I have had the program look at the entire corpus and pick out the 15 most frequently occurring words. Okay, and ignore everything else. Okay, you can just assume that you go through the entire corpus and remove all words except the first 15, except the most frequently occurring 15. And if you do that, then you can show word vectors in this way. Okay. It is really a terrible thing to do, to throw away so many words. And I'm doing this only to explain to you what term frequency means. So when we proceed further, we are going to set this number. We are going to change this from 15 to a more realistic number. Okay, we will do that. But for now, let's just leave it at 15. Okay. So I think you have understood that this simple trick of simply counting words and the frequency of their occurrences can convert a block of text into a vector. Okay. This is the simplest way of doing it. And I know I can already hear people complaining that what? Then word order is totally messed up. Yes, it is messed up, but it may be good enough for our purposes. It's good enough for information retrieval. It's good enough for text classification in most situations. Okay. Now, it's possible to do better than this. Okay, instead of considering individual words, you can consider pairs of words. You can think of a pair of words as one entity and count the number of times that pair occurs. That would be better. If you like, you can count the number of triplets and so on. All those are possibilities, but we'll keep it at the barest minimum level. Okay, so now you know how a block of text is converted to a vector. Okay, so let's just take a look and understand this better. You see, I told you that we limited it to the 15 most uh, important words. Okay, we can take a look at what those words are. Okay, and we can even see um, the importance. Okay, so the importance is shown here. Okay, what are the words that got thrown away by this process? Remember, this is not like stop words, but simply because we limited our vocabulary to 15, we limited it to 15, then a whole lot of words got thrown away. You can take a look at everything that got thrown away if you like. Okay, so all of these words got thrown away. Okay, we are not going to do this terrible exclusion down the road, but this is just to explain how text is converted to vectors. Okay. Now I want to explain the concept of document frequency. Okay. There may be some words, and by the way, when I say words, I also mean terms here. Term and word are the same, at least as far as this notebook is concerned. Term is more general because term can refer to either word or word pair or word triplet. It can even refer to a character. Okay. But as far as now we are concerned, we are thinking of terms as words. Now, you may find that certain terms may occur in all documents indiscriminately. Okay, we would be right in thinking of those words as not important, because you cannot use those words to tell apart one class of document from another class of document, right? So that would be bad. You know, I wish we had two-way communication here. So I would be able to ask you, which of these words do you think qualifies to be uh, not informative because they occur in too many documents? Of course, this word, including, we can expect it to occur in a whole lot of documents. It has probably very little to do with the category, right? So the word also, okay, uses, but not biology. We can expect that the word biology does not occur in all documents, because why would the word biology occur frequently in a document about commerce? Okay, it's possible, but it may not occur frequently, right? So there is the concept of document frequency, right? When we say document frequency, you can understand it by looking at this. Okay, this tells you that the word also occurs in 1521 documents, and the word including occurs in 1465 documents, okay, and so on. Whereas words like biology are less frequent across documents, okay. When we say less frequent across documents, we mean that the word biology does not occur in so many documents. So it must be an important word, okay. That's the concept of document frequency. This is the document frequency vector, okay. You realize that if you see a big number here, that means that word is not important, right? So if we want to get a sense of inverse importance or lack of importance, you can consider inverse document frequency, which is the reciprocal of this, okay? So these are the reciprocals. That's called inverse document frequency, okay? So you have already understood the meaning of term frequency and inverse document frequency. Why are we bothered about inverse document frequency? I'll tell you why. We are bothered about it because, you see, this is our initial attempt to convert every block of text to a vector, okay? We have done it, okay? But if we just go with this representation, we are not going to get a good classifier, okay? So we need to do some massaging of this matrix. And what we are going to do really is take each of these numbers and either emphasize or de-emphasize depending on inverse document frequency, okay? So that's exactly what we want to do. So you compute the document frequency, take the reciprocal, find the inverse document frequency, okay? This is what you get. And after you do that, it's also, I'll skip this part, okay? But you can see here, all I'm doing is I'm taking the term frequency and multiplying it with inverse document frequency, okay? If I do that, you get these real numbers. You started with integers, but now you have real numbers, okay? It might seem to you that art has been somehow de-emphasized, okay? And the word century has been de-emphasized, but biology has been emphasized. Well, that's what is in our corpus, okay? That is representative of our corpus. Who knows? We haven't really taken a detailed look at our corpus and understood the spread of various words there. So whatever you're seeing here is what it actually is, okay? Now there is another thing that you need to do, again, by way of making better and better vectors, Okay. All of this stuff also sounds like pre-processing, but it is pre-processing of a different type compared to the earlier types of pre-processing that we did. So in this type, what we need to do next is make sure that, or we need to recognize that a certain block of text may have a whole lot of words repeated in it. The word, I may have a big block of text, which is all about biology, something about some animals or fish or something. I may have another short document also about biology, which has far fewer words totally. Okay. I want to be able to still say that this big piece of text, which is about biology, and this little piece of text, which is also about biology, they are similar. I want to be able to make that statement. So if I want to be able to make that statement, I need to somehow normalize every vector with the length of that document itself. Okay. Or in other words, I have to make sure that every vector which I'm showing you here, every vector should have the same length. Okay. So if I somehow get that normalization done, then my different documents are going to be still informative, whether they are long or short, as long as they contain the right words. Okay. So this is another type of normalization which you need to do. So we can do that. We can make sure that every vector has unit length. Okay. I've done that. And here I'm just showing you, yes, these 10 out of thousands, I'm just picking out these 10 vectors, indeed have unit length. Okay. I want to tell you that everywhere here, I'm doing all these computations from scratch. Okay. Which is against the dry principle, right? So, well, that is bad, as I said. So, because we have a package called TF-IDF vectorizer, you can get exactly the same result as before. That's a good thing, right? So I'm just demonstrating it to you here. If you use this TF-IDF vectorizer, then it's only one line or two lines. You can do that entire vectorizing, okay? And over here, I'm just helping you convince yourself that you get exactly the same results, whether you use the package or whether you use it by breaking it up and going through each sub process. Okay. And that is good sometimes just to get an understanding of how things are done. So we have about 15 minutes more. Okay. So we are kind of almost done. So now we need to get real. See, so far, I just limited the number of terms to 15. Okay. Because we wanted to just understand all of these steps without having our head spin. Okay. But now, if we understand that, yes, we don't need to visualize these tables, we don't need to visualize these numbers, we can just understand that, yes, vectors are being created. Okay. Now you can increase the number of words in the vocabulary from 15 to 1000. Okay. 1000 is a lot. Okay. Now you can create your vectors. I'm just calling it X. So you see this entire block of vectors, 4991, you have 4,991 documents, and every document has been converted to a 1000 dimensional vector. Okay. So, well, you can again ask the question, what are the terms? Yes, you can figure out what the terms are if you like. You can take a look at all the 1000 terms if you like. I'm just showing you the last 10 terms. Okay, they are arranged alphabetically. So I'm just showing you the last 10 terms that have been retained. A whole lot have been thrown away, of course. Okay. Now, remember, I said that you would want to insert your own text here. Okay. And check if the classification is correct. Okay. So in order to do that, it is good if I write a function which can do all of this stuff, pre-processing and this vectorization, right? So that's exactly what I have done. Okay. I have created this function called query to vector. Okay. It can take a query, it does the pre-processing, it does the vectorization, and it just gives you the final vector, which is 1000 dimensions. Okay. I'm just checking to make sure that it is working, right? So now we are in a good place because we have converted that entire corpus. Every document has been converted to a vector. So as I said before, all the usual machine learning methods can be used, okay? Like prediction, classification, and clustering. They're all possible, right? So, I'm just following the traditional workflow here. If you want to do text classification and make sure that um, you're above criticism, you need to break your entire corpus or entire training data. I'm sorry, you need to break all your data into a training set and a testing set. You build your model or you build your classifier using the training set. And if you want to know how good that model is, you use your testing set. This is the usual machine learning workflow. Okay. So this is how you break your data. Now we are calling our data as X, right? So that's what we did here. You see, we created X using all of the documents that were de-tokenized. Okay. So once we get this X, you can see here, I'm taking this X and breaking it into a training and testing set of vectors. But I'm also keeping track of the class labels. Okay. So the training labels and testing labels are available here. So if I want to build a classifier, it's very easy. Okay. I can just use scikit-learn's logistic regression classifier. Okay. So use that package called scikit-learn. Very, very indispensable package. Okay. You can create a classifier and test it all in just a few lines of code. Okay. And upon testing, you see that it is 90% accurate. Okay. Which is very good, right? So that's how you build a text classifier. Okay. Um, let's see if I have a little time at the end, I can just take a random piece of text. I can just copy and paste from any website and try to see if it can classify it. I'm not sure if I'll find time to do this, but I invite you to try it, and your results, I'm sure, are going to be interesting. Okay. Let's move on to information retrieval. Okay. Now, talking about information retrieval, again, let me go back to this picture, or I can just uh, do a new one here. Remember, I told you that every block of text is a vector, right? So if we are talking about vectors, there is the concept of similarity. Okay. So I'm sure you understand that these two vectors are similar to each other. Okay. Versus these two vectors. These two vectors are much further apart. So these are similar, these are not so similar, right? So if I'm given a query, okay, let me try to draw a query here. So if I'm given a query which is here, Okay, that X is a query. In order to answer that query, I have to just look at this closest vector. Okay, if this is the query, then I need to somehow find this vector, which I've marked with an arrow there. And I have to go back and look at the class or the category associated with that vector. Okay, that's how information retrieval works. Very simple, right? So as long as I have the ability to find the closest vector, I have the ability to find the class of the closest vector, I have the ability to answer that query. So that's what we are going to do. So if I'm given a query, I have to first, that query is just natural language. I have to first convert it to a vector. Okay. Once I convert it to a vector, I have to check the distance between that vector and all the other vectors in the corpus. Okay. So I'm calling this similarity scores. And once I get the similarity scores, I can rank. Okay. I can find the indices of documents that are closest. Okay. For example, here, let's try doing this. Let's take document number 15. We have been going with document number 15. And if you just want to see what is document number 15, you see here, it's a document that has something to do with biology. And this is the document. Okay. This is just straight data. I'm just looking at the data. But now, if I, let us say, use that very same document itself as a query, this is just to make sure that the system is working. If I take that very same document itself as a query and find the matches, okay? And how do I find matches? Yes, by computing distances, by ordering those distances and so on. So if I compute all the matches, yes, you see that the top match, of course, is the very same document, okay? If I did not get this result, I should be very worried. Of course, the top document is the very same input document. But interestingly, you can see that the other documents, okay, are all related to the top document. Okay, they are all different documents, as you can see from here, but all of them have something to do with biology. Okay, and they may not, if you closely look at all the documents, you may find that they may not have the word biology in them. Okay, but still, overall, there is the concept of distance and everything works out wonderfully. Okay, so I hope I have left you with some understanding of how natural language processing works. Okay, this is barely scratching the surface. You can do a whole lot of wonderful things with this. Now let me just look at the questions flowing so far and see what I can help you with. How do you define the distance between vectors? That's a great question, really. The distance between vectors is, there are so many ways of doing this, okay? Euclidean distance, cosine distance, and so on. So as long as you understand that when you say vector, you're talking about vector with real numbered, real valued components. You can always find a distance between those vectors, okay? And in our case, we use something called cosine distance, okay? And that is anyway available to you if you use the package scikit-learn. That's automatically available to you, right? So you don't have to reinvent the wheel there. How do you label your input text if the labels are not available to begin with? So this is a question asked by Rupa. I think I do remember Rupa. So hello and good to see you again virtually. Yes, that would be unsupervised learning. So you can have a bunch of unstructured text and do clustering and come up with clusters. And once you have those clusters, there is a way actually to look at the words in those documents and perhaps come up with the answer to the question, what is the salient word associated with that cluster? Okay. It's once again all about geometry, finding the centroid of that cluster, finding the word which is closest to the centroid, and so on and so on. Okay. I hope I have answered your question. And how do you capture the position of individual words in the sentence? Um, how do you capture the position of individual words? If that is important, I'm sure we can figure out ways to do it and we can talk about it. Okay. Um, I can always think about associating, you know, to each word, let's say you append some extra text, which gives you the position of that word. You can always do that. Okay. Or NL toolkits available for languages other than English? I'm happy to say yes, they are available. And if you take a look at a package called GenSim, I'm quite sure even NLTK has multi-language support, but I'm very sure that GenSim has support for many languages, and you can do a whole lot of these type of things using GenSim. Okay. Do these NLTK packages work right out of the box with non-English text? Yes, as long as the language is supported, yes, it does. Okay. Can you give an example of what a term looks like? When we say term, we mean word. That's all, word. As far as our examples are concerned, term means the same thing as word. Okay. So if you apply PCA on the raw vectors, wouldn't it eliminate the noisy information in your example? Oh, this is such a great question. I really, really appreciate it. Mr. or Ms. Anonymous. There is another technique very similar to PCA that's called singular value decomposition. And as far as natural language processing is concerned, there is a technique called latent semantic analysis. You can do amazing, amazing things using latent semantic analysis. And it's also based on the principle of dimension reduction, or as you have said, removal of noisy information. Okay. You can do wonderful things with that. Yes, the answer is yes, you can do that. Is there a best way to extract paragraphs in a text or PDF file? Uh, are there any off-the-shelf packages? Yes, there are. You know, uh, I think just a few minutes with Google or Stack Overflow will help you with this. For example, if you have text on various websites, you have you have a package called Beautiful Soup that you can use. In fact, I use Beautiful Soup in order to create this corpus, which I'm sharing with you. I harvested data from Wikipedia, and I was able to use this. Now, I think I remember Akshay Agarwal, who is asking me this question. Is there any way we can distinguish special characters and normal words in non-English languages? So again, if that language is supported, then the special characters must be marked. Okay. If they are not marked, then you can try building a classifier. Okay. You can take it as a challenge if you want to do um, this to a language which has not yet been absorbed into NLTK or GenSim. You can try building a classifier to do this. Can this be used to find specific sequence from genome sequence? Absolutely, yes, you can. In fact, natural language processing has made possible so many tools which are used in biotechnology, in DNA sequence analysis, and so on. And uh, actually, in my class, I try to demonstrate that using um, short sequences of DNA nucleotides and presenting a classification problem. Using the string of nucleotides, can you identify the animal or insect that it represents? Okay, so uh, my students enjoy building a classifier that can find the name of that animal. Okay, so the answer to this is yes. Would you be able to share sample code for that? Uh, if you could please remind me. Uh, you see, I'm not sure if you were present in yesterday's. Um, you have my email address here. If you remind me and ask me for that piece of code, then I'll be happy to share that with you. You're talking about code that distinguishes various animals from DNA sequences. But I must warn you that, um, you know, that code resulted from a project that I did, and I was not allowed to actually share that real data. So the data that you will see in that notebook is fake data. It is fake, but it demonstrates the concepts. And Anonymous, thank you very, very much for these kind words. So I have another question. Is it necessary to filter stop words and do stemming? If that can be avoided, would the later steps be language independent? Um, so I'm not sure if I follow the connection between language independence and stemming, but I can tell you this. I'm going to make this notebook available to you, and you will find that it is so easy to answer questions such as this. Okay, you can always very quickly, you can tweak this code taking no more than 10 minutes, and the effect will be that stop words are not filtered. Okay, and you can check the accuracy of your classifier, and perhaps you will find that the accuracy is slightly less, not significantly less, but perhaps slightly less. You see, we should also keep in mind that ours is a very small corpus. So you may not see a big difference. But if it's a big corpus, then you get a huge advantage by throwing away stop words. And that's something to consider always. Okay. So thank you very, very much. I hope you enjoyed this. And I hope I'll see you again, either in a classroom or somewhere else. Okay. Bye bye for now.